Hey everyone, I'm Kathy Zip, Senior Editor of Solar Power World magazine, and I'd like to welcome you to today's webinar, Distributed versus Virtual Central String, Application Matters. And today we're going to look at some of the different string architectures that are used in large projects. You kind of understand how those affect system costs as well as how you can optimize your next project with the right architecture. So before we begin, we'll go over just a few general items. This webinar will be available after the presentation on demand. I know a lot of people ask that, so you can access it on solarpowerworldonline.com, but you'll also get an email since you registered for this webinar, and you can view it again at your convenience. You can also download slides from the resource box, and there will be a question and answer session at the end of the presentation, so we encourage you to participate. You can just submit questions at any time during the presentation in the Q&A box on the bottom of your screen. And we do encourage you to engage in the conversation on Twitter with the hashtag SolarWebinar. And so I'll introduce today's presenter. Today we have Sarah Ozga, Product Manager of Chint Power Systems North America. Sarah went to Arizona State University for mathematics before beginning a career in solar 10 years ago. She worked in PV system design and installation before working with her inverter manufacturers, so she understands many of the challenges that installers and developers face and will help to try to solve some of those today. So Sarah, go ahead whenever you're ready.
Thank you very much. And thank you all for joining us today. I'm Sarah Ozga. I'm the product manager here at Chint Power Systems. And I have one of our applications engineers, John Drummond, here with me as well. He's going to help me answer some questions at the end that you guys have for us. But we have a lot of information to cover, and I'm sure we're going to have questions at the end. So let's get started. Now, here's what we're going to be looking at discussing today. First is that breakpoint between string and central systems and how we got there. After going through what we learned from this, I will not be mentioning central systems again. Everything from then on will be distributed string and centralized string architectures. If you're here today because of that buzzword virtual central, don't worry. A virtual central is just a way of applying a centralized string system, but it's not the only way. After we get the layouts, we'll look at some costs associated with each architecture and the losses as well. We'll put this all together side by side to compare to help you figure out which may be the best approach for your next project. So before we discuss distributed and centralized architectures, it's important for us to understand how this conversation developed. Years ago, string inverter manufacturers, we made this big push into the commercial market by introducing 1,000-volt string inverters into the commercial market, and we were taking central manufacturers head on. And string manufacturers, including CPS, are pushing again by introducing 1,500-volt inverters and saying that we're ready to be a part of the larger utility scale market. The string versus central paradox mostly resulted in people saying, if a project is less than 5 or 10 megawatts, I'll do string. If it's greater than 5 or 10 megawatts, I go central. Occasionally we see that breakpoint as high as 20 megawatts, but accepting that breakpoint, wherever it was, 5 to 10 or even at 20, we needed to understand why. So we asked, why that system size? Why don't you use string inverters above that point? And why don't you use central inverters below that breakpoint? The reason we need to understand this was to determine if string inverters could make an impact in large utility scale projects. So let's take a look at the pros and cons. One more time. All right, here's what we heard. The common pros and cons from installers, developers, site owners as to why they chose string or central for their sites. If we were to find a way to bring string inverters to that greater than 5 to 10 megawatt space, We needed to solve some of these real concerns. All the positives are displayed in the green check marks and the negatives with the red arrows. The common disadvantages string inverters had were higher O&M, long AC runs, higher inverter costs. But we had an opportunity here as well. On the central side, we would hear multiple combiners and recombiners, less system visibility, and larger downtimes. So a string manufacturer set out to solve some of our own shortcomings when it came to utility scale. Now, central inverters are no longer a part of this presentation. Everything from here out, we will be comparing distributed and centralized string solutions. So let's start with how distributed string systems solve these challenges, since up until now, these have been the most common application of string inverters. I think there's a little delay, so give me a moment here. There we go. So we're at higher O&M costs. When you spread inverters through a field, it will take more time to service. And let's just hope that your as-built are up to date so you know where you're going. Higher O&M is related to the cost of servicing a greater number of smaller inverters spread throughout the array as opposed to fewer and/or centralized inverters. In larger utility scale sites, the time alone to traverse the field from one inverter to the next is costly, but these 1 to 10 megawatt smaller systems are much more manageable. So that breakpoint we discussed, or that 5 to 10 megawatts, that makes sense here. In order to help with cutting O&M costs, we believe reducing the time to perform an inverter swap can be very valuable. Replacing a typical string inverter in the 100 or 125 kilowatt size can take an hour to disconnect each conductor, make sure they're properly secured or capped off for safety, and then remove the inverter. And installing products with a separate inverter and wiring box will allow the service person to remove the inverter section without disconnecting any conductors. This allows for a 15-minute inverter swap and does not require a trained electrician because no wiring is exposed. When the inverter manufacturer has a service portal capable of remotely updating firmware and troubleshooting, you prevent site visits. Whether service is performed by a customer or a manufacturer, this saves time and gets the non-operational units back generating power faster. And here's a depiction of the 100 and 125 kilowatt string inverter and how that power head swap is done. All of the wiring is done in the right side of the wiring box, AC and DC conductors, and that power head just slides right off. So no wiring is needed to be removed. Now, how do you solve the long AC runs on distributed string systems? Well, today you don't. Long AC runs are inherent to distributed string systems. What we can do is take a page from central inverters and increase the output voltage. This reduces the current and requires smaller conductors. But when we talk about longer AC runs, we're talking about the cost. But are AC conductor costs really in these systems as bad as you think? Well, maybe not. In a few slides, we're going to compare some of the system designs that will show the cost difference between the distributed and the centralized systems. These 1500-volt string inverters are much less expensive than their commercial 1000-volt counterparts. You'll see this across multiple manufacturers. At 1500 volts, these inverters don't need boost stages to increase their DC voltage before converting to AC. Designing the inverter with one MPPT and no LCD screen further reduces the cost. But we can only reduce the cost so much in these inverters. So we look for ways to reduce the system cost. A major expense in distributed string systems is communication wiring, and this can be tens of thousands of dollars in some cases. CPS distributed wire box versions include PLC communication to completely remove the communication wiring cost. And lastly, the inverter wiring box. Now, this isn't anything new, but consider that an inverter with a combiner box raises the cost of the string inverter $300 to $500, whereas external combiner boxes can cost anywhere from $750 to $1,300. All right, now let's discuss the negatives when it's applied to the centralized string systems. Centralized systems aren't new. Designers and installers have been aggregating inverters for years, like in the picture on the bottom right. And now we look at centralized systems using string inverter skids, or containers, which we call virtual centrals. An example of the virtual central is shown on the top right. And this one is a containerized version. Now, back to the solutions. Starting again with higher O&M costs, with a centralized string solution, you're grouping the inverters close to the point of interconnection. This can be achieved using a virtual central, which you see used in traditional central inverter systems. A virtual central will include a skid, inverters, AC switchgear, and a transformer. This certainly will raise the cost of the system as much as 2 to 2.5 cents per watt. But what we gain from this is an easier O&M plan on potentially very large sites of 20, 50, 100 megawatts and more. And with the potential of having the AC wire from the inverters to the switchgear and or the transformer pre-wired prior to being dropped on site, we are saving installation later as well. But what if you don't have a site that will support a skid? Drop in a few posts, create a frame on Unistrut, like in the picture on the bottom right. And this is referred to stick building a virtual central. And that's being done in very large applications right now. These inverters are lightweight and can easily be supported on a strut frame. Just build the frame close to the transformer pad. And finally, again, you see service portal bullets. I cannot stress this enough. Whether distributed or centralized, make sure your inverter can communicate with the manufacturer remotely. Troubleshooting and firmware updates performed remotely can greatly reduce the downtime in truck rolls. In the past, around 50% of service actions were related to firmware updates and improvements. Solving the longer AC conductors is easy. And centralized string means that we are installing the inverters in a group or on a skid close to the point of interconnection. Just like longer AC runs were inherent to distributed string systems, short AC runs are inherent to centralized systems. The cost. Centralized version of string inverters will be the lowest cost among string inverters because they do not include the DC combiner or wire box. This cost can be somewhere around $300 to $500 per inverter, but this isn't necessarily lowering your system cost. Remember, you still need external DC combiners with this type of architecture. Now we are transferring the cost from the inverter to the balance of systems, and external combiners can cost $750 to $1,300. And remember, too, that 1,500 volts is still relatively new for North American solar in general, not just string inverters. There are not currently a massive selection of 1,500 volt combiners on the market today. But hopefully, as more enter the market, the prices will come down. But we will never see them as cheap as they are when they're integrated in the wiring box of an inverter. So when we compare the distributed and the centralized systems, we can see how the different architectures stack up against each other. PLC is a standard feature of CPS distributed wiring boxes on the 100 and 125 kilowatt inverters. This is not available from all manufacturers, so when you're estimating the system cost, remember to account for this if using another brand. I can't speak to other manufacturers' products, only the design concepts and what CPS is doing to help reduce those costs. So now looking at these side by side, we can see the difference is longer AC runs versus multiple DC combiners. So now it's time to look at the different designs and costs associated with them. There's a little bit of a delay, so I just want to make sure that we get to the slide that we're going to be talking about. There we go. So CPS has developed a model comparing the cost differences in various architectures at 1500 volt DC. Our applications engineers worked with consultants and some of our customers to get information on configurations, general pricing, and practices. Wire cost was determined at the time based on the market and frequently changes, but it is all relative and will produce similar delta between the system types, so don't get too hung up on the pricing. This is not an exhaustive synopsis of the entire report that we developed, but an overview of some of the more surprising and impactful results that we found. What we are focusing on are conductor and DC combiner costs, because we identified in the previous slides that those were some of the pain points that exist in centralized and distributed systems. What we didn't include was racking and module costs, because this is going to be constant between the different systems. Now, labor is very much not constant and varies by state and company, so it's too varied for us to represent in a way that could apply to everyone here. When using string inverters in any of these systems, you will need AC combiners. The cost will change somewhat based on the system type chosen, the block size, but there are so many options we could choose. We just chose to use the same AC combiner in each scenario. We also did not include conduit, trenching, and SCADA. The first architecture that we're going to look at is the centralized string option 1. The system has DC combiners out in the array field, and the inverters are at the point of medium voltage conversion. The inter-array wiring is not included because this is going to be consistent between each of the system types that we're going to look at today. We have calculated the average length of conductors between the string and DC combiner to be 200 feet. The variable we'll be looking at is the home run. We have calculated the wire cost of various home run lengths, taking a 2% voltage drop into consideration, and used a cost of $1,200 for the external DC combiners. At this point, the block size we're designing with does not make a difference for what we're evaluating. It will eventually, and we'll discuss that, but what matters here is the length of the home runs. But in the entire analysis performed, we did look at a 2 to 3 megawatt block sizes. Now, the table displayed, as soon as I can get it displayed, the table here tells us what the cost per watt of that DC home run plus combiner box will be. The first column is the length of the home run. This is why the block size we're using doesn't make a difference. If you're using a 2 megawatt block, your conductors will be shorter than using a 3 megawatt block. Layout will make a difference too. For a particular site, determine the home run length, and we know what the cost per watt is going to be. The third column is labeled factor, and this is what determines the wire sizing. The NEC has a sizing wire based on what size the overcurrent protection device would be or would need to be in order to protect that circuit. Then we determine the voltage drop and size up from there. In each of these cases, the 400 MCM conductors are sized by that overcurrent protection device rule. As you can see in the last column loss, that voltage drop is well below 2% in each one of these cases. Now, there is nothing surprising here. As we increase in length, the cost goes up, but we're going to put this all together in a few slides when we compare our different systems. Don't worry about taking any screenshots to grab pictures at this time. We're going to lay it all out for you. The next system is distributed string. We're removing the external DC combiners and replacing them with a standard wiring box version of the string inverters. This is what you may consider a typical distributed string system. Again, the inter-array wiring is not included because this is consistent between each of the systems, and the average length of conductors between the string and the inverter is 200 feet. Remember, we're looking at the home run distance. The distributed string system wire cost will be from the AC conductors, since our inverters are out in the array field. These inverters have a 600-volt AC output, so they will have about a 20% lower current than you would have if you were using a 480-volt string inverter, which means smaller conductors. Now, here we see that once we get up to that 350 feet, the overcurrent protection device is no longer the factor controlling the wire gauge. In order to keep the voltage drop below 2%, we have to keep increasing the wire gauge as we go farther distances. A few of them were slightly above 2%, but we left those instead of upsizing. The yellow highlighted cells are each time we needed to upsize due to the voltage drop. The final configuration, if we can see it, there we go. We're going to look at the centralized system, but using inverters with distributed wiring box. This was not one of the more traditional ways to design centralized systems, but it's starting to be used more now in larger systems. Here we include the previous 200-foot length from the string to the DC combiner or inverter in the total home run length, since there is no longer a combiner or inverter in the field breaking up the PV source, PV output, or inverter output circuits. Here you can see, as soon as we get there, now we can see that even though we are running multiple string conductors all the way back to the point of medium voltage conversion where our string inverters are, we don't need to upsize until we reach 750 feet. Even then, it's only a change from 12 gauge to 10 gauge. But beyond that 750-foot distance, the cost starts to get pretty high. So now let's compare the three architectures side by side. We're showing the lowest cost in green and the highest in red. I numbered the system types up on the top with the description so we can keep those straight. From 250 feet to 750 feet, the optimum system types are the distributed string and centralized string with the standard wire boxes, or systems 2 and 3. In fact, the cost is very similar between these two system types until we pass 700 feet. Remember, 700 feet or 750 feet is where we started upsizing the conductors in system 3. It isn't until we get to the longer runs that the centralized system using DC combiner boxes out in the field really makes sense. That was system 1. What this is telling us is using the external DC combiner does not pay off for us until we reach an 800-foot home run distance. If you're using a 2 megawatt building block, that is 16 of the 125 kilowatt inverters and 16 combiners depending on the architecture you chose. At $1,200 each for the combiners, they would cost $19,200. But if we use inverters with a standard wire box, eliminating that $19,000 external combiner cost, we would be spending about $5,000 more for the inverters. So that's a savings of about $14,000. Okay, up to this point, we have been looking at the architectures with respect to wiring and distances. But now let's see how this data applies to the block sizes. Almost there. There we go. Here we have the data from the previous slide, all plotted. The blue line is the centralized system 1, red is the distributed string system 2, and the yellow is the centralized string with the standard wire boxes, or system 3. Now we have a visual that shows us until we get to 750 feet, the centralized system 1 has the highest wiring cost. Systems 2 and 3 using the standard wire boxes and centralized and distributed architectures are very similar in cost until that 750 foot mark. Between 750 and 850 feet, systems 1 and 2 are pretty close in cost. Then the centralized system 1 is the clear winner at the 900 foot and longer distances. Now on top of this, we added 4 vertical lines. The darker blue vertical lines represent the average minimum and maximum home run distances of a 2 megawatt block. The green vertical lines represent the average minimum and maximum home run distances for a 3 megawatt building block. Now we can see for 2 megawatt block sizes, systems 2 and 3 are the better options until we reach the max calculated length of wire runs for that size block, or that dashed blue line. In the 3 megawatt block size, between the 2 vertical green lines, it's clear that system 3 is significantly more costly halfway through the average 3 megawatt block size lines, and only in the very upper margins of this 3 megawatt block do we see the centralized system 1 come out as the leader. We added the trend line on the red distributed string curve to show that it's not linear and it's actually exponential. If the graph extended, we would see it eventually pass our yellow system 3 line. At this point, the data is showing us the centralized string option doesn't compete well with wire cost in the 2 megawatt block. And it's only a clear winner when we exceed the average max home run distance on the 3 megawatt block. This is a pretty important slide, but it isn't the only results that we can pull out of the data that we used. So let's go back to the chart because we have more to discuss. Okay, so we're going to discuss losses. There we go. Here again, we have the lowest losses highlighted in green and the highest in red. There is a difference between the DC and the AC losses because we oversize systems DC to AC ratio so significantly today at 1.4 to 1.5. We're pumping more DC watts into the inverter than it can utilize. Looking at the power curve at the top right, we remember that the higher the ratio, the wider that curve is. We reach the point where the inverters start clipping power earlier and stays there later when more PV power is delivered to the inverter. 1.5% DC loss will slightly narrow the curve, but not be a 1.5% loss in total power because we haven't even reached that peak yet. Once we do reach the peak, or clipping red line, that DC loss is immaterial because the inverter can't process all the energy it receives anyway. But AC loss is a little different. The AC losses are directly related to revenue loss. The inverter has already converted the DC, so those losses aren't fixed by raising the DC to AC ratio, but a similar curve still applies. At 9 a.m. on a south-facing array, we are not producing max power. A 1.5% loss on a 1 megawatt array is not 15 kilowatts at that moment. It would be 1.5% less the power the inverter would be producing at the moment based on the DC input power, which is much less than peak. So which is better? Well, you can offset DC losses, so using the PV source or output circuits to make up that home run we calculated will result in less losses than if you ran the AC conductors, which means systems 1 and 3 are better when we're discussing losses. They're both the centralized architectures. We've discussed wiring and combiner costs and losses. There we go. But there are other factors in choosing a system type. While we cannot cover every one, the transformers are a big cost in any system. Choosing the 6 megawatt AC site, we randomly picked 2 architectures and block sizes. The first is a 2 megawatt block using a centralized string architecture that has a standard string combining wire box. This was system 3. The average wire distance for a 2 megawatt block in this system is 600 feet. The second was a 3 megawatt block using a distributed string architecture, which was system 2. The average wire distance for this 3 megawatt block is 750 feet. Using a 1.5 DC to AC ratio, we have the wire cost in the right column of the top chart. The 2 megawatt block ends up being about $60,000 less in a wiring cost alone. Now, transformer costs will vary based on many factors, but we included here some sample pricing of 2 MVA and 3 MVA transformers. Because we need more transformers when using 2 megawatt blocks, the total transformer cost is about $13,000 more for the smaller block sizes. When we take these 2 costs into consideration, the 2 megawatt block size still ends up being the least expensive of the 2 chosen, and in this case by about $47,000. So if you joined us today thinking that you are going to get the answers as to how to design all your large systems going forward, I'm sorry. There are clearly a lot of variables to this decision. A few we didn't directly discuss here were AC switchgear and the cost of the virtual central skid, should you decide to buy one rather than build one on site. What I can tell you from the research that we've done is that the optimal cost of the switchgear appears to be below the 3 megawatt size. There is a limit to the standard ratings of equipment, and combining 3 megawatts of string inverters is pushing it today. As for virtual central pricing, there are so many options available that this will be customer or even site specific as well. From years of discussing string versus central, we know the advantages of using string inverters, but how you apply the string inverters in a site makes a huge difference to your system cost. Now, the CPS 1500 volt inverters are available with either centralized or distributed wiring boxes, so depending on which architecture fits your next project, we can support you. Now, that was a lot of information in a brief presentation, but we want to help you. We don't want to just sell you inverters here at CPS. We want to make sure that your systems are going to be designed efficiently and as safe as possible. So you can call us and we can walk through your site designs and variables with the models that we have spent all of this time creating and presented a piece of for you today. So we're here to help. Thank you very much.
Thank you, Sarah. That was wonderful. A lot of information to digest, so I'm sure that our audience has some questions. In fact, we have a few already coming through. So just remember that you can continue to submit your questions in the Q&A box at the bottom of your screen, and we'll begin asking some of those here. So someone is asking, they say they usually design distributed systems because they need to distribute the weight in a larger area. So what do these 1500 volt string inverters weigh compared to central?
Yeah, absolutely. So central inverters in the 2 to 2.5 megawatt range, they can weigh anywhere from 8,000 to, I think I've seen some as much as 15,000 pounds. And that is a lot of weight to put in one area on a site, especially in some of these areas where it might be more marshy land or have restrictions. But the CPS 125 string inverter with the full distributed wiring box will weigh 175 pounds. So at 2.5 megawatts, we're looking at roughly 3,500 pounds for 2.5 megawatts. That's anywhere from 4,500 to 11,500 pounds less. So quite a significant reduction in weight on these string inverters compared to central inverters.
Absolutely. Another question is, do the large 1500 volt systems need arc fault, and do CPS inverters have that?
Yes, so the 2017 National Electric Code has a new section in it from previous editions of the NEC, and that's section 691, I should say. And in 691, that's meant for large-scale PV plants. There is an exception to the arc fault rule as long as you have an arc fault mitigation plan. But not everybody wants to or is able to go through that. So they would require arc fault on those sites as well. The 100 and 125 1500 volt inverters at CPS, we are developing arc fault in it, and in fact we've been working very closely with the certification agencies. The setback there is that currently all of the listings for arc fault are only up to 1,000 volt DC inverters. That change is coming, and it will be coming very soon. The testing has been written, and we're going through implementing that in the standards. And since we're working so closely with the listing agencies, we're working to already comply to those before they're published. So yes, we will have a listed 1500 volt DC arc fault, but as of today, it is unable to be listed because the listing only goes up to 1,000 volts.
Okay, got it. Thank you for explaining all that. Another question is, the plants that I install usually need to provide reactive power support to utility. The owners don't want to sacrifice real power, so they use central inverters. But can the string inverters provide reactive power without sacrificing the real power?
Yes, and that was the reason people used central inverters primarily for sites like this for a very long time. It's only been recently that some string manufacturers have started providing what we call KVA overhead, and our 1500 volt inverters do provide this. So what that means is when a utility company has a requirement that you operate at a power factor other than 1, say 0.95, you're going to need to be delivering reactive power. And if you don't have that KVA overhead built into the inverter, that's reducing your active power output of the inverter. And the active power is what we get paid for, or what you get paid for. It's the real power. Now, the 1500 volt CPS inverters, the 100 kilowatt in particular, will operate at full nameplate rating, full active power, all the way down to 0.91 power factor. And the 125 kilowatt inverter, that will operate at full nameplate output rating down to 0.95 power factor. So you can still produce that reactive power without compromising your real power.
Okay, we have a couple more here. Someone's wondering about some resources on maybe your website, maybe some sheets or data sheets on especially detailing the centralized versus distributed wiring boxes.
Sure. Yes, so our 1500 volt products are set to release in just a couple months from now. Right now we have the data sheets, manual, OND files, all of that right off of our products page on the website. I do not currently have a paper on comparing the differences between the distributed and centralized wiring boxes, but that's actually a really good idea, and I'll get working on that.
Nothing like some inspiration from the audience, right?
Absolutely.
Good feedback. I think we have time for one more question. Someone's wondering if the inverters interface with cellular data connection.
Okay, so sorry, I was taking a note on our last comment. Cellular data communications. The 100 and 125 are not built in with cellular communications. It operates either on the RS-485 Modbus, or if you don't want to wire the site, then we have the option of the power line communications in the distributed wiring box versions. Now, if you are looking at taking your data off the site, the transmission of the data, we work with all of the third-party communications monitoring companies, like Also and Locus and those guys. As well as if you are a company that manages your data yourself, rather than going through third-party systems, we have a product that is called the Flex Gateway. And what that is that's one card installed in just one inverter in that Modbus communication loop, assuming you're using the Modbus. And we can pass through that data directly to the customer's data management system. I haven't seen that too much in some of the smaller to medium-sized companies, but more and more customers are starting to look at managing their data themselves as opposed to going to third-party sites. That's a very powerful tool. You're not paying other companies to manage it for you, and you own the data rather than renting it. So the Flex card allows you to do that. But if you're looking at needing a cellular transmission to get the data off of the site, then we generally partner with third-party monitoring companies for that.
Excellent. Okay, well, I think that's all the questions that we have time for. But if we didn't get to your questions, you can contact Sarah on your own. And we hope that you enjoyed the information. Again, this webinar will be emailed to all registrants, so you can view it again at your convenience. And Sarah, I just want to say thanks again for all the great information. You know your stuff.
Thank you very much, Kathy. I appreciate the time.
Sure, and thanks again to our audience. You can register for other upcoming webinars on solarpowerworldonline.com. Thanks so much, everyone.